A solution is generally defined as a homogeneous mixture of different components. When one component is present in larger concentration than any other component of the mixture, we call this major component the solvent and the minor components the solutes. When a solution is homogeneous, it exists as a single phase, where the distribution of solvent and solute is the same throughout the solution. While the concept of solution can be applied to solids and liquids, we will focus our attention on liquids in this lecture. By analogy with the gas mixtures discussed in the Fundamentals chapter, we can characterize the composition of a solution of solute B in solvent A using the mole fractions of A and B. The mole fraction of a component in a mixture is simply the number of moles of that component divided by the total number of moles of all components in the mixture. Note that the sum of the mole fractions of all components must be equal to 1. While chemists often like to use mole fractions, this may not always be very practical, especially if one of the components or a smaller mass is unknown. So, in some instances, the composition can be given in terms of weight percent of the different constituents. The sum of the weight percent of all constituents must equal 100. For gases, we can often specify the composition of a gas mixture using the partial pressures of all components. Partial pressures are a measure of composition because they can be related to the mole fraction of that component in the gas phase using Dalton's law, which we discussed in the Fundamentals chapter. Another measure of the composition that is often used in chemistry laboratories is the molarity or the molar concentration of the various solutes in solution. The molarity of a solute B is defined as the number of moles of B per liter of solution. We say that a solution is 1 molar in B when the solution contains 1 mole of B per liter of solution. Another common measure of concentration of a solute B is the molality of B, which we define here by the symbol small b of B, and which is defined as the number of moles of B divided by the mass of solvent used to make that solution. When calculating weight percent, mole fraction, molarity, or molality, it is of utmost importance to be very specific about where the species are, that is, either in the solution or in the vapor phase above the solution. Because even at equilibrium, the composition of a solution differs from that of the vapor above it. Note that all compositions are intensive properties that are independent of the amount of solution considered. When you calculate a molarity or molality, you need to always pay attention to the quantity in the denominator, and remember that molarity refers to a given volume of solution, not solvent, while the molality refers to a specific mass of solvent, not solution. To relate the molality of a solute in a solution to its molarity, or vice versa, requires that you know the density of the solution. Again, it is important to remember that the solution density is the ratio of the mass of the solution to the volume of the solution. The mass of the solution is always the mass of solvent plus the masses of solutes. We will see shortly that the same relationship cannot be applied to the volume of the solution.